Good morning students. Today we will discuss about extrinsic semiconductors or the bond and band structure of extrinsic semiconductor. So as we have discussed in earlier classes, what is extrinsic semiconductor? Extrinsic semiconductor means it is the doped semiconductor. It is the doped semiconductor means in intrinsic semiconductor we add impurities. So extrinsic semiconductor means this is the semiconductor in which charge carriers originate from impurity atoms. See here charge carriers. What are the charge carriers in semiconductors? Electrons and holes. So these charge carriers will be originating from impurity atoms. We will get from impurity atoms. So those are called as extrinsic semiconductors. So, depending on the nature of impurity doped, means depending on the dopant impurity, semiconductors are divided into. See here, depending on the nature of impurity doped in intrinsic semiconductors, okay, extrinsic semiconductors are divided into two types, N-type semiconductor and P-type semiconductor. Okay. First we will discuss about N-type semiconductor. Now see here, what we will do is for intrinsic semiconductor means for pure form of semiconductor we will dope with pentavalent impurity. Pure semiconductor, intrinsic semiconductor is doped with pentavalent impurity or fifth group element. So what are the examples of fifth group element? Antimony, phosphorus, arsenic, bismuth. So when we dope this fifth group element into intrinsic semiconductor. Now intrinsic semiconductor, what are the examples for intrinsic semiconductors? Examples for intrinsic semiconductors are silicon and germanium. So how many valency electrons does they have? They have 4 valency electrons, but we are doping with pentavalent impurity. We are doping with pentavalent impurity means it is having 5 valency electrons. So in order to attain stability, this silicon and germanium requires 4 more electrons. It requires 4 more electrons, but we are giving 5 electrons. Here in order to get octet configuration 8, it requires 4 more electrons, but you are doping with 5 electrons. Okay. So see here, this 4 valency electrons makes covalent bonds with 4 electrons and 1 electron, fifth electron is left free. So see here, when pentavalent impurity or fifth group element is doped into intrinsic semiconductor, then 4 valency electrons of impurity atom make 4 covalent bonds with 4 intrinsic atoms and fifth electron is left free. So you can see in the bond structure. See here, this is the intrinsic semiconductor. You can see the bond structure. So see here, these are the germanium atoms which are tetravalent, means which are having 4 valency electrons. Now it is doped with fifth group element. Okay, arsenic, it is doped with fifth group element. So all these are plus 4, tetravalent, and we are doping with fifth group element, means it is having 5 valency electrons. So in this 5 valency electrons, 4 valency electrons will be going for sharing and fifth electron is left free. This fifth electron is left free. Okay. Then see here, this is the pentavalent impurity. What are these? Tetravalent atoms. Next, what are these? Valency electrons. And what is this? Covalent bonds. These are the covalent bonds. Okay. Now, if I dope with one fifth group element, I got 1 electron. So if I dope here also, if I dope with arsenic, fifth group element, so what happens? I will get another free electron. So as as the impurities are increasing, the number of free electrons are also increasing. So here this arsenic means fifth group element, pentavalent impurity, is donating electrons. It is donating electrons. It is giving electrons, donating electrons. That's why this is called as donor impurity. Here this arsenic is called as donor impurity. And these electrons are called as donors. These electrons are called as donors. So what happens as the donor impurities increases? Donors also increases. So see here, this free electron is called as conduction electron. As these free electrons are donated by pentavalent impurities, they are called as donor impurities. Okay. So semiconductors doped with pentavalent impurities are called as n-type semiconductors. Next, as donor impurities increases, what happens? The number of electrons also increases. So here electrons will be more when compared to holes. Here electrons will be more when compared to holes. So what are the majority charge carriers in n-type? Electrons. Electrons are the majority charge carriers in n-type. So this is about bond structure. Now if we go for band structure, so we can see the band structure. So this is the band structure. See here this is the valency band and this is the conduction band. We know that at T is equal to 0 Kelvin. At T is equal to 0 Kelvin, valency band is filled with electrons and conduction band is empty. Okay, now these are the valency electrons, but 1/5 electron is left free. Free electron, 1/5 electron is left free. Where does it stay? See here, it stays in donor level. Fifth electron lies in, one extra electron lies in donor level. Okay. Now at T is equal to 0 Kelvin, valency band is completely filled. And this we call it as donor level, represented by ED. Donor level is also filled with electrons and conduction band is empty. So this is the case at T is equal to 0 Kelvin. And you can see the diagram, where does donor level lies? Donor level lies just below the conduction band. Donor level lies just below the conduction band. Okay. Now if I give temperature at T greater than 0 Kelvin, what happens? At T greater than 0 Kelvin, this electron moves from donor level to conduction band. Donor level to conduction band. Okay. Leaving holes in donor level. Leaving holes in donor level. So at particular temperature, what happens is all donor electrons get jumped to conduction band. Now donor level is empty. Here electrons from the donor level, they are jumping to conduction band. So at a particular temperature, donor level becomes empty. Still you are giving temperature. Means you are giving still temperature. So what happens? Now electrons move from valency band to conduction band, creating holes in valency band. Now these holes in the valency band are responsible for conduction, and electrons in the conduction band are responsible for conduction. So you can see the diagram. So number of holes in conduction band are more, number of electrons in conduction band are more, or number of holes in valency band are more. So electrons are more in conduction band. So that's why majority charge carriers are electrons, because electrons in the conduction band are more when compared to holes in valency band. Okay, when you got hole, this hole is created in valency band when you give temperature. That's why these holes are called as thermally generated holes. Okay, means thermally generated minority charge carriers. So this is about N-type semiconductor. Now, next, if we go for P-type semiconductor, in P-type semiconductor, see here intrinsic semiconductor. Here intrinsic semiconductor is doped with trivalent impurity or third group element. Means trivalent impurity means which are having 3 valency electrons. 3 valency electrons. In intrinsic semiconductor, you know, they are having 4 valency electrons. It requires 4 more electrons to get stability. It requires 4 more electrons. But how many are giving? You are giving only 3. You are doping with trivalent impurity or third group element. For examples, aluminum, gallium, boron, indium. So when I dope this, any of these elements, okay, it requires 4 more electrons but doping with 3 electrons. So what happens? One vacant space is left. Okay. So when a trivalent impurity or third group element is doped into intrinsic semiconductor, then 3 valency electrons of impurity atom make 3 covalent bonds with 3 intrinsic semiconductor atoms, leaving 1 vacant space. So in the fourth bond they leave 1 vacant space, that we call it as hole. So here germanium intrinsic semiconductor is doped with boron. It is doped with boron, that is trivalent impurity. So in one bond there is a vacancy, hole. So this hole is ready to accept electrons. These holes are ready to accept electrons. That's why these are called as acceptors. What are these called as? Acceptors. And this impurity we call it as acceptor impurity. This impurity we call it as acceptor impurity. Okay. So as the acceptor impurities increases, what happens? Acceptors also increases. So if I dope here also boron, so what happens? Here also 1 vacant space will be left. So as acceptor impurities increases, number of acceptors also increases. Means number of holes also increases. So what are the majority charge carriers here? Majority charge carriers will be holes, because holes will be more when compared to electrons. Okay. So see here, trivalent impurity accepts an electron from valency band of intrinsic semiconductor. That's why they are called as acceptor impurities. So semiconductors doped with acceptor impurities are called as P-type semiconductors. So as the acceptor impurities increases, what happens? Holes also increases. So you can find more number of holes than electrons. So holes will be the majority charge carriers. So this is about bond structure. This is about bond structure. Now if we go for band structure means it will be having valency band, conduction band. Okay. If I go for band structure, so see here, this is the valency band. Valency band at T is equal to 0 Kelvin. So valency band is filled with electrons. It is filled with electrons. Next, acceptor level. This hole exists in acceptor level. So at T is equal to 0 Kelvin, valency band is completely filled with valency electrons. And acceptor level is represented by EA. Acceptor level is filled with holes. Holes means it is empty because they are vacant spaces. Next, conduction band is empty. Already we know conduction band is empty. Okay. Now, so when you give temperature means at T greater than 0 Kelvin. At T greater than 0 Kelvin, what happens? The electrons, here hole is ready to accept electrons. So the electrons move from valency band to donor level, forming holes in valency band. So, okay. So electrons move from valency band to acceptor level, acceptor level leaving holes in valency band. After some time, so at particular temperature you can find that whole acceptor level is filled with electrons. No more vacancy, no more hole. Still, if you give temperature, means on further increase of temperature. So on further increase of temperature means still if you give temperature, what happens? The electrons move from valency band to conduction band, leaving holes in valency band. So you know that which electrons are responsible for conduction? Electrons present in conduction band. Which holes are responsible for conduction? Holes present in valency band. So if you see, valency band is having more number of holes than electrons in conduction band. So that's why majority charge carriers are here. Majority charge carriers are holes. So where does acceptor level lies? Acceptor level lies just above the valency band. Acceptor level lies just above the valency band. So this is the band structure of extrinsic semiconductor.